I believe this is the last lecture I'm giving, because the student lectures start next week, and then it goes into the project presentations the week after, and then we've concluded the week after that is bust, which is ridiculous, but it is what it is. So this is the last lecture I'm giving. Of course, obviously you are all required to show up for every student lecture and everything. That should go without saying. But PSO, all right, particle swarm optimization. It's, okay, so in the world of evolutionary computation, that's a big category. And within them, we have things like evolutionary algorithms. I know, like, the terminology is kind of obnoxious. Evolutionary computation, there's evolutionary algorithms. That's things like your GA, your differential evolution, your genetic programming. But we also have another category. There are several categories under evolutionary computation, but another big category under evolutionary computation is swarm intelligence. And the biggest form of swarm intelligence is particle swarm optimization, PSO, they call it. It consists of particles, and every individual particle acts independently, but is influenced by the whole population. And by the way, like evolutionary algorithms, like, for example, a basic genetic algorithm, all of this is simply a loose guideline. As soon as you find yourself asking the question, but could I do? Yes. What if I want? Yeah, go ahead. It doesn't matter. You can do whatever you want. This is a loose framework, all right? So what do we see here? Well, there's like birds flying around. And what's interesting about this picture here is each bird, like, I think what's happening is these birds are flying away from like a predator. I think if you look closely, I think there's like, you can see, like, there's a bigger bird. I don't know. Maybe, I could be wrong. They might be flying away from a predator. I don't know. Either way, they're like swarming. So each bird is acting independently of one another, yet they are clearly influenced by one another because there's some sort of like pattern going on. But they don't share like some cognition. They're acting independently, but they are affected by the whole population. PSO, I'm just going to call it PSO, is a form of evolutionary computation that works really well, and it's like effectively it's been designed to work with real numbers or floating point numbers. And it's like a lot of forms of evolutionary computation, the basic idea is relatively simple to implement, even relative to other forms of evolutionary computation. It's got very few hyperparameters to tune, and in fact, there's a lot of people that say that some of the hyperparameters that there are there, you really don't need to tune them. You just kind of set them and forget them. So that's kind of nice. And it's given its simplicity, along with a lot of the other forms of evolutionary computation. Because it's simple, it's easy to extend and add your own ideas, because it's also like very modular in the same way that genetic algorithms are. So the first thing we're going to talk about is the particles, each individual particle. PSO consists of a population, just like a genetic algorithm has a population of chromosomes. Here, we will have a population of particles. And these particles represent points in some high-dimensional search space. This is going to be hard to kind of see what it means in general, so we're going to eventually be talking about a very specific concrete example, and perhaps it's a little contrived, but the concrete example is going to be, we're going to have some. Here, let me jump ahead. Do I really not have a good picture of this right now? Damn it. All right, well. Okay, maybe I won't spoil the fun. All right. All right, so where was that? Unlike chromosomes, these particles do not make use, like the algorithm doesn't make use of the typical variation operators. It doesn't have a crossover. It doesn't have a mutation. But it has something that is effectively those things. If you think, by the way, an aside to this, if you think long and hard about PSO, you're going to come to the conclusion that that's like basically a genetic algorithm, though. You're absolutely right. It really is. If you think hard enough and you dig hard enough, you realize it's the same goddamn thing. But it's at high enough of a level, and the way we make use of it, they feel different. So These particles are influenced by the population, the whole population. And this is the base framework. You can have like hierarchies. You'll see what I mean as we get there. They have a propensity. Each particle has a desire to move. Each particle has a velocity, okay? It's moving through this high-dimensional space. And the example we're going to be talking about is going to be a two-dimensional space. Think of it like I'm moving through this two-dimensional space. I realize it's 3D, but I'm on a plane, this floor, and I'm looking for the hottest point, okay? And I'm looking for that hottest point in here, all right? I'm moving around. So I've got 2 dimensions, and the dimension I'm like optimizing is temperature, right? Obviously, it's not in the same plane. It's different. So yeah, these particles, they have a velocity, but they want to move towards what it liked and what the population liked, right? Think of it like this. Here's the idea. I'm walking and I'm looking for the hottest area, and I feel a really warm area here, okay? And by the way, I'm in a room full of people who are doing the same thing. We're all kind of walking around looking for the hottest area, okay? And I feel the hottest area here, and I'm like, oh, it was hot over there, so I'm going to kind of like go back that way. But I see everyone else is kind of moving over there, so I'm like, oh, well, it was hot here. Well, let's, like I'm kind of moving around. That's the idea. Okay? Questions or anything at this stage? Pretty early. As you can see, a remarkably simple concept. Something that, hell, this is how you do shit, right? If you're looking for something and you saw something was good over there, like, I don't know, like, you're looking for a good reference for your paper. And you're looking through all these references and you're going through it. And you found a really good one, you save it maybe in a tab. And you start looking at other ones and you're like, I don't really like them. I'm going to go back to the other one I liked. And maybe you go there and then you look at what side. Like you kind of go back to what worked good for you. But if you see everyone else somewhere else or like, oh, they use some other reference, you might go like, oh, that's interesting. What are they doing? Like you're influenced. Everybody in here is influenced by what I like. And I'm also influenced by like what everyone else likes. That's the idea. It's a core basic idea that you are all familiar with because we kind of do this in our everyday life. So in terms of an optimization problem, each particle has a propensity to move towards the best area of the search space it has encountered, while also having a propensity to move towards the best part of the search space that the population has encountered. This would then assume that each particle is aware of the best point, like each particle knows the best area it was, like the best area it encountered, and it somehow obviously like magically knows the best area everybody else has encountered. Obviously, I can't read a mind, so I don't know what the best one was. In practice, we'd kind of make use of just observing what everyone else is doing to get a sense of what everybody else likes. And each particle has a velocity and an inertia. Long story short, like, it's not going to just like jump to the best area. It's like moving, and then it's got like a momentum, but it might be like it'll like rubber band back to where it wants to go. So here's a little GIF showing what's going on, right? 3 to -3, -3 to 3. And this is a minimization problem, okay? So what we are viewing here, if you're having a hard time seeing it, this is the two-dimensional space, and it's almost like we have like a topographical map, right? Where, like right now, this area is a very low point. If this was three-dimensional, like imagine I took this like this. We've got the two-dimensional space, but this part in the middle is like low, okay? And these parts are really high. So you kind of get a sense, it's actually kind of like a wavy three-dimensional space, okay? And each of these x's, along with their arrows, is where they're moving. So each x is a particle, and its arrow is like where it's moving. And this is a very simple, silly little example. But you can see, as it starts, they're all kind of doing their own thing. But see how they kind of like move towards what worked, right? Like this guy's stuck in a local minimum, right? It can't jump over that hump, right? Because this is like it can't figure out how to go there. That's okay. But most of them are kind of like hanging out around here. They're like, hey, we found the good spot, right? Neat. Like this guy. Are they going to go? Come on, come on. Oh, no. Anyways. Does that make sense? Questions, thoughts, concerns, comments, anything? Representation. PSO is typically, it's kind of like what it's designed for. It's to work with real numbers. So whenever you have a problem with real numbers, this is great. You want to use something like this. Each particle is typically represented by an n-dimensional vector encoding its position in that high-dimensional space, in that n-dimensional space. For example, in the above figure, each particle would represent a three-dimensional vector. Actually, well, so two-dimensional plus its in the above figure. Two-dimensional plus its like z coordinate, I guess. I feel like maybe I should really call that two-dimensional. I'll fix that later. Each particle has a position in its space, representing as an n-dimensional vector containing a position in space. So the particle's position at time t. Velocity, which is also represented as an n-dimensional vector containing deltas. So that's the velocity. Each particle is going to know the best position that it encountered. Okay, it's another n-dimensional thing. And it has access to the swarm's best known position in n-dimensional space. So the particle knows where it is. It knows its current velocity. It knows the best location it's ever found, and it knows the best location anybody in the whole population has ever found. Cool? Cool. Velocity. The velocity determines where the particle will be at the next time step, right? This is an iterative algorithm, right? So if I'm here and my velocity is 1, I'm going to take like 1 step to make it to the next time step. It's velocity, right? It's the change in where you are, okay? As the algorithm executes, the velocity of the particle is going to be changed, though. So obviously, the position of the particle is going to change. But its velocity is going to be changing also throughout the execution of the algorithm because it's being influenced by, like, I want to go. I have that propensity to go to where I liked and where everybody else liked. So the velocity is changing, okay? So not only is my position changing, my velocity is changing. Just like we can observe in this example up here, right? The particle's position is clearly moving, but like the arrow is its velocity, and it's changing too. Like they're moving like all over the place, right? Yeah? Okay. The velocity calculation. Well, velocities are typically initiated with some random values. So the particle's position is going to start at some arbitrary location. And its initial values are going to be randomly determined, right? Probably within some defined range. You don't want the velocities to be like 1 billion, right? That's ridiculous. You want them to be like some reasonable number given the domain of your search space. But the algorithm, the velocity particles change. Okay, each particle has some velocity. When particles' velocities are, did I repeat myself there? No, okay, perfect. Each particle has some velocity. When the particle's velocities are updated, the changes are applied to an already moving particle. These particles want to continue moving the way they are. So this is like this inertia term, meaning my velocity is going to be updated, but I'm not going to just like, if I'm moving like this and I want to go there, I'm not going to stop and go straight there. Imagine I'm running really fast and I need to make a hard right turn. I can't do a 90-degree turn. I'm going to fall over if I do, right? It's not possible. I kind of have to like run and like turn, right? Like I've got some like momentum, okay? Like I have to deal with that. That's what this is. This is this idea, okay? So I have some inertia. I have a propensity to move towards what I like. I have a propensity to move towards what everybody liked. And I also have a propensity to keep moving the way I was moving because of my inertia. So each particle has some velocity, but when particles' velocities are being updated, the changes are applied to an already moving particle. That's the idea. If I'm moving like this, I can't just start moving that way like that. I have to, I've got to kind of rubber band to where I'm going. Do you know what I mean when I say that? So these particles want to continue moving the way they are. They resist change. So thus, the first part of the velocity update, okay, we're talking about, okay, the particles are being moved by their velocity, and the velocities are changing. How are the velocities changing? Well, here's how. The first part of the update for a velocity is its inertia term. We have this expression where the velocity, my current velocity, okay, so a particle's current velocity at some time step. Are we happy? Yeah. And we have some coefficient. This is one of the hyperparameters we pick. Some coefficient of inertia. I make this bigger. I'm going to dominate any update to velocity by the inertia. My current velocity is going to dominate any update to the velocity. If I make it smaller and smaller and smaller and smaller and smaller, it's going to be easier for me to change my current velocity. I'm realizing this is difficult to explain because this should be painfully obvious to you. If it's not painfully obvious, tell me because I need to figure this out. Okay. If this is my speed, if my speed is 10, this way, right? And I want to update and let's say I want to move, my next step, my velocity update wants to go like this, okay? So 10, right? So I'm running that way, and at the next instant, I want to turn around. Okay, I want to immediately, effectively, if my velocity is 10 that way, and I want to make my velocity 10 that way, that means I want to stop, okay? If this is 0, my velocity update, okay, v I at t plus 1. So at the next time step, okay, if it equals whatever I want my velocity to be plus 0 times this, that's just 0. Meaning, if my inertia coefficient is 0, that means I can stop instantly. One sec. If I crank it up, it's harder. It's harder for me. I can't instantaneously stop. What were you going to say?
Does it make it just like your coefficient of friction?
I'm not sure if it would be exact. I'm not sure if it would translate exactly to that. I'd have to think about that. Why am I having a hard, maybe if I show you the whole thing. You're a boat, okay? Can a boat stop like that? No, it ain't gonna happen, right? It's got inertia, it wants to keep moving, right? So if I'm moving 10 that way, and I wanna move 10 this way at the next time step, if I have no inertia, I can stop. I can immediately stop, okay? If I have an inertia of 1, meaning my next velocity is going to be this, yeah, I can't move it. I'm stuck, right?
Yeah.
Okay,
the one thing I'm trying to wrap my head around is your omega is between 0 and 1, but you want to go the other way.
Yeah.
So it goes to stopping point, and then what are you resetting and doing it again? Because it can't be negative.
My inertia?
Yeah.
No, or you mean my velocity can't be negative? My velocity can be negative.
No, but the coefficient. Because if you're using it to go to stop, and then you're saying the next step, it's going to
Well, this is my velocity. Okay. Let me do it like this. Maybe doing the different directions was a problem. If I'm moving like this, okay, and then I want to move like this, 10 like this, 10 like this, okay? If a one-time step, like, it's also, I guess it's difficult because we're talking about velocities, not where the particle position is, okay? If my inertia is 0, after the time step, my velocity won't be that anymore, it'll be that, okay? But if my inertia is 1, after that time step, my velocity is that, okay? If it's between 0 and 1, why are you smiling? Am I getting it wrong?
I just don't understand.
Maybe if I explain the whole thing, it'll be a little clearer to you. Maybe if I had a more concrete example too. Give me a second, let me think if that'll work. Look, it's my inertia. I'm speeding down the highway going like that, okay? If I crank the wheel like that, is my car going to go straight like that? No, that's ridiculous, right? I'm going to go like that. I'm going to curve. Why? Because I'm already moving that way, and my body like resists change to going that way. So like I'm going to keep going that way a bit, right? How much am I going to go like that? That's what I control with this. That's what's happening. Cool? Happy? Happy or not? Okay, cool. Cognitive term. Okay, each particle also wants to move. So this is the velocity update, right? So there's the first part of the velocity update is how much am I resisting change? How much do I want to keep going the way I was going? The next part is how much do I want to go towards the best thing I've seen so far? So they call this the cognitive term. The name of it's arbitrary, but they call it the cognitive term. And we see C1, R1, P best, whatever. Basically, this is the difference in the best location I found and my current location, right? So the further away I am, the bigger this is going to be, right? The bigger the difference. I've got this R1, that's going to be some random, this is where like the stochastic nature comes in. That's a random vector. I just randomly generate some numbers that are going to be bounded by something reasonable. And C1, where C1 is a hyperparameter I control that says, how much do I want this to matter? It's a scalar, basically. If I make C1 0, how far away I am from the best thing I've found so far means nothing to the velocity update. I add 0, right? If this is a bigger number, it matters more and more and more, okay? So if I'm updating my velocity, if I make this 0, okay, let's establish a few things here. R1, that's the randomness. That's where we add a vector. Do I say R1 is some stochastic vector discussed below? Where do I discuss it below? Okay, maybe further below. The further away I am, imagine this is constant, doesn't matter. The further away I am, the bigger this term becomes, meaning think of it in the context of like a bigger velocity update where we have like the next velocity is going to be the inertia term plus how much do I want to go towards the best thing I've seen so far. The further away I am, the more I want to go towards like the thing, the best thing I've seen so far, right? Like I'm getting further and further away. I really want to get back there, okay? If all things being equal here, if this was 0, I don't care how far away I am anymore. Whether I'm really close or really far away, I don't care anymore. All right, so each particle wants to move towards the area of the search space it prefers, the best known location for the particle. And so that's where we go, where I is some particle. C1 is some coefficient used to control how much the particle is influenced by its best known position. It's usually between 0 and 2. The higher C1, the more the particle is influenced by its best known position. R1, P bet, yeah, whatever. Okay. The difference between the particle's best known position and current position dictates where the particle needs to go. The delta there. C1 and R1 scale the vector. So if this is where I currently am, this is my best known location, I want to move towards there. Okay? But remember, like let's say my current velocity is like this, right? So if I want to start going towards there, I can't just, if I have inertia, I can't just stop and move towards there. I'm going to keep wanting to go that way some amount, right? So I'm going to like curve because I'm being influenced by that. You look like, I don't know. You're okay? Okay. And then there's the social term. How much I'm influenced by the global best known position, right? And we have the exact same thing. It's how far away am I from the best known position of everybody. I have some scale and some randomness involved too, okay? So the whole expression is this, okay? V t plus 1, right? I'm influenced by how fast I'm currently going. I'll call that the like inertia plus my local plus global, right? So I am here, moving like this, right? Best known location for me is here. But the global best known location is here, okay? Let's say, can you all see this reasonably well? Let me lower this, maybe it'll make it easier to see. So, that's my current velocity, right? So I want to keep going that way. I also want to go that way a little bit. And I want to go that way a little bit. Well, I can't do all three. I need to add these vectors together, okay? If we take these vectors, like if my velocity is if I add these together the way it is, I end up over there, right? That's where but what I'm doing is I'm scaling these vectors. How big or small am I going to make that vector? That's that like little omega. C1, C2. How much am I scaling those vectors, right? These are getting bigger and smaller, and it's going to change its final destination depending on how I scale these things. Also, don't forget the fact that we've got this randomness involved too, where it's basically like a perturbation to each particle's like current, how much it really wants to go there. It's like perturbed a little bit. That's where we get a little bit of exploration. Okay, speaking of, the cognitive and social portions of velocity update include this R1 and R2 thing. The vectors have a value between 0 and 1. So we have vectors of values between 0 and 1. I guess they could be, no, we want them to be 0 and 1. These are randomly determined for each velocity update calculation for each particle. This is where the randomness gets involved within the iteration of the algorithm. And these random stochastic vectors are important as they add a chance for like novelty, exploration to the search space. Although there's a lot of things in here that are exploration, but this is a really great way to add some novelty. And they just also show to empirically they work goddamn well. So the velocity update is going to be the sum of the parts of the update. My speed at the next time step is going to be based on where I'm, like how fast I'm moving in my current direction, how much I want to go to the best thing I've seen so far, and how much I want to go towards the best thing anyone's seen so far. Cool? All right, as discussed, there are 3 coefficients that need to be tuned for the algorithm. Turns out, some people are pretty comfortable saying like, just use these numbers. You could change them, but people are saying like, just use these numbers. They don't ask me, they just do. Yeah?
I have a question. Is always this velocity update positive or could be negative? In order that the velocity is reducing?
Well, the velocities can be negative because it's always, yeah, like the velocities can be negative, yeah. Because like, think about it. If my current point, like if my, they can be, it all depends on where we are. Like if I'm here and I want to go here, right? Like I want to move towards that location. So the negativeness is all about like directionality. Yeah? So yeah, they can be negative. Yeah. But don't, do you remember, we're talking about like vectors. So this is about like the direction of the vectors. Yes?
Why do we want our C1 and C2 to be the same?
I don't know. I don't know. If you ask Vandenberg, they'll tell you. It's in here somewhere. It was their PhD thesis, I think. Oh, Engelbrecht, I know him. I met him. He doesn't know me. Okay, position update. Well, that's easy. That's where I currently am plus my velocity. There you go. So consider the below figure. The particle's current position is represented by the green vector. Right here, that's my current position. Particle's velocity is represented by the blue vector. So that's like my velocity, meaning like, well, I'm actually like, right? You add the vectors together. Yeah. Cool? Remember, this is vectors. Go back to grade 12. You did vectors in grade 12, right? You're not so sure. You're pretty sure you did? If you don't know what look, if you don't know what vectors are, don't worry. All you have to do is remember grade 2. You just add them together. You take like, if I wanted to add, you take this and go, and you just like add them together, right? If you had the vector 4 and 7, and I wanted to add it to the vector 1 and negative 2, right? So 4, imagine we're in a, like, you know, 4, 7, 1, negative 2, right? We've got 2 vectors, right? Right? Well, let's just add, okay, that's 5. You do like, you know, you just do the addition. 5, 5. So that would be like about, I don't know, here, right? And you're like, well, how would I, well, if you just take this, let's pretend that's the same, because I can't do it that accurately without a grid, right? So you just kind of like stick them together. It's just like, that's all, right? If it feels complicated, it's not. And if you're like, but I didn't understand that, that's fine. Happy? Sad? Angry? So the algorithm. Well, here's the whole algorithm. It's remarkably simple. Initialize the particle's positions randomly. Initialize the velocities randomly. Well, the stopping criteria is not met. What's the stopping criteria? Whatever the hell you want it to be. Number of iterations, find a good enough thing. It's the same thing as a GA. Well, the stopping criteria is not met. For our particles, evaluate the particle's fitness. Update the particle's global best if necessary. Basically, did I find a new like best location for anybody? And then for all particles, calculate the particle's new velocity, update the particle's position. That's all. That's it. That's it. If you're like, that's too simple, it really is. It may not be immediately obvious, but look for the similarities between this algorithm and a genetic algorithm. Initialization, generational loop, fitness evaluation, variation operators. Their major differences are that there's no real selection as all particles are survived, but they're all like influenced with one another. Although this is a selection strategy. And the velocity and position updates are not mutations or crossover, but consider the cognitive and social aspects of velocity updates. The cognitive kind of is like mutation, and the social's kind of like crossover. Like there's like internal changes, like something that only really affects me, and then there's the social, which is like it's influenced by otherness. These are variation operators. So simple enhancements, like this is a very basic GA. There's a lot of things you can do here, right? So we have a social and cognitive thing, right? Where I'm influenced by my best location and the global best location. Why not add like a neighborhood where you've got like subsets of particles, where you're influenced by the best thing I found, the best thing my like neighborhood has found, and the best thing the whole population has found. Sure, go for it. You can bound it, where you basically set rules where you can't like go too far outside of a domain, which is just a good idea. Velocity clamping, this is a really good one. Don't let the velocities get out of whack. Kind of like bound the velocities such that they can't get bigger or smaller than a certain value. The same thing with the positions, I already said that. Charged PSO, this one's a pretty cool one, where the particles actually avoid each other though. Where they basically, they want to go towards the best position they found, and they want to go towards the best position anybody's found, but I don't want to get too close to any other particle. So we kind of like, we keep our distance, right? So I have a propensity to move towards the best things I know of and I've been told of, while also having a propensity to move away from other people. Which is weird, right? You're like, they seem like they counteract each other, but in practice it works pretty damn well, and you can probably kind of figure out why. So how do we implement it? Well, first we would need a problem. And there is a Wikipedia list of example toy functions for real number optimization. All right? So we're going to use the Matthias function. This is the function. It's a two-dimensional problem where the third dimension will be like f of x and y. I want to find, I'm guessing this is a minimization problem. Yeah, it's a minimization problem. I want to find the x and y values that minimize this function. The best answer is 0, 0. We're dealing with floating point numbers, meaning you ain't going to find 0, 0. But the best number is 0, 0. Okay, this is the function. It's a very concave problem where like it kind, we kind of want to move towards what's good, which is nice. It's a simple problem to select. But there we go. This is the function. Okay? This is effectively the fitness function. I want to minimize this. So each particle is a two-dimensional vector. It's a pair of numbers. You plug the x and y into this, you get a number. You plug another particle's x and y into it, which one had a smaller number? The one that's smaller is better. Hey, right? That's what we want to do. Cool? Well, here's the implementation of the Matthias function. Yeah, it's that. Yeah, that's just the function. Initialization. Well, I'm going to make the particles dictionary, a list of all the particles. There'll be a list of dictionaries for the dictionaries. Instead of making a whole class, I'll just use a dictionary to store each particle's position and velocity. And each particle will also have a best known position. And yeah, there we go. Cool? Cool, cool, cool. For those of you that don't know, this would be what like one would call like a data class, where like it's a class that really is just like, who here is familiar with C, C++? Remember structures? Structures? It's just data, right? There's no functionality here. It's just storing some data. It's a data class. So each particle has its position. It's a randomly generated. Its starting velocity, randomly generated, bound by some like bounds. Okay? Like we don't want the random positions to be too big or too small. Its best known location will start as its current position. And yeah, there we go. Cool? Yeah? Some values I have. Function dimension is 2. There's some bounds. Number of particles is 10. Iterations 100. And my inertia in cognitive and social terms, they're all just set based on what Vandenberg told me to do. We can play with, I want to be clear, play with these. When you're doing that, if you're doing assignment 3, play with these numbers to see what happens, right? But these are like a great place to start. Evaluation, well, for each particle in particles, the value is going to be, well, call the function with the location, the position. If the particle value is, I'm minimizing here, if the particle value is less than the best known position, then my best known position, update it. If it's not, ignore it. If my value is better than the global best known position, I update it. It's that simple. If you're like, wait, what? It really is that simple. Each particle knows its position. All right, throw that position, that x, y coordinate, into the function. That's it. That's it. That's it. Calculate its fitness. Okay, then update the velocities. Particle. Get the R1, R2. The particle's velocity is, well, the inertia times my current velocity, plus the cognitive coefficient, R1, times the difference between my best known location and my current position, plus the social R2 and the global difference as well. Yeah. And then update the position by, well, the position is equal to my position plus my velocity. And that's it. That's really it. Any questions about that? So how does this all go together? Well, throw it in a loop. For however many iterations, evaluate the particle's the particle's position's fitness value. If the particle's fitness value, we just looked at this. I'm just showing it you again. If its new value is better than the best I've seen so far, update the best I've seen so far. If it's better than the global best one, if it's better than anything I've ever seen before, update the global best. Then, update the velocities and the position of each particle. Repeat. Repeat, 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 repeat. That's it. And then when you're done, well, I've got this whole swarm. How do I know which one's the best? I save the global best. The global best position is stored right here. When I'm done, I just print out global best. Boom, I've got the global best position I found. Print global best, and then you can get its fitness by, just calling the fitness function. This is PSO. It's so goddamn simple. So goddamn simple. If it didn't click, if the intuition behind how it worked didn't click, just look at it again slower, and you'll probably get it. I was obviously trying to move a little quick today, but yeah. Yeah. You had a question? Oh, I thought you did. All right. Raise your hand if you're doing a lecture for the class. 1, 2. Okay. And the other people aren't here, I guess. Just to be clear from the email yesterday, you can use PowerPoint. You don't need to upload it to the course website. You can if you want, but you don't need to. Cool. Sorry?
I was going to ask about that. But
Cool. All right, cool. Any last questions? All right, I'll see you all Tuesday for, who's presenting on Tuesday? You? I look forward to, who else? Do we know?
Carson.
Maybe. Well, anyways, they better be here.